They're the biggest names in chocolate, but what really happens behind factory walls is more intense than you'd ever imagine. From massive mixing vats to high-speed molding machines and secret flavor formulas, this is industrial chocolate making on a jaw-dropping scale. In this documentary, we reveal how Hershey's, Cadbury, and Mars turn raw ingredients into the world's most iconic chocolates. The production of Hershey's chocolate, from raw cocoa beans to the smooth, creamy bars found in stores across the globe, is a finely tuned industrial process that combines traditional chocolate-making techniques with large-scale factory automation. The journey begins with the sourcing of raw ingredients and extends through roasting, grinding, conching, tempering, molding, and packaging, all carefully orchestrated to deliver Hershey's signature taste and texture in every bar. The process starts at the very beginning of the supply chain, the harvesting and sourcing of cocoa beans. Hershey sources its beans primarily from West Africa, including countries like Côte d'Ivoire and Ghana, where cocoa trees grow in tropical climates. Once harvested, the beans are fermented under banana leaves or in wooden boxes for several days. This crucial step develops the deep chocolate flavor. After fermentation, the beans are sun-dried, sorted for quality, and bagged for export. Upon arrival in the US, Hershey's manufacturing facility inspects every shipment, checking for size, moisture content, and the absence of mold or pests. The beans are then conveyed into the cleaning and sorting machinery, where they pass through vibrating sieves, pneumatic suction tubes, and magnetic separators. This removes twigs, stones, dust, and any metallic particles. The cleaned beans are stored in large silos, kept dry and temperature controlled to preserve freshness. From here, they enter the roasting stage, which is one of the most important parts of flavor development. In the roasting stage, cocoa beans are fed into large rotating drums that heat them to between 120 and 150 degrees Celsius for about 30 minutes. The temperature and duration are carefully adjusted depending on the bean variety and flavor profile desired. During roasting, volatile acids are reduced and deep chocolate notes are intensified. The process also loosens the shells from the nibs, the edible inner part of the bean. As the roasted beans exit the drums, they move into the winnowing machine. The winnowing process uses high-speed fans and friction rollers to crack the roasted beans and separate the lighter shells from the heavier nibs. The result is a large volume of cocoa nibs, the pure form of chocolate, which are then transferred to grinding mills. These heavy-duty industrial grinders reduce the nibs into a thick, brown liquid called chocolate liquor or cocoa mass. Although the term liquor might sound alcoholic, it refers here to the liquefied state of cocoa solids suspended in cocoa butter due to the heat generated during grinding. Next, Hershey separates the chocolate liquor into cocoa butter and cocoa solids using hydraulic presses. The cocoa butter is a pale yellow fat that contributes to the creamy mouthfeel of chocolate, while the cocoa solids are rich in flavor. Hershey stores both components separately in stainless steel vats. For milk chocolate, which is the company's primary product, the recipe also calls for sugar, milk, lecithin, and flavoring ingredients like vanillin. One of Hershey's defining characteristics is its use of fresh milk, a distinguishing factor that sets it apart from European chocolatiers who often use powdered milk. In fact, Hershey operates its own dairy processing facilities in Pennsylvania. The milk is condensed and cooked with sugar to form a sweet, caramelized base that's blended with chocolate liquor and cocoa butter. This mixture is the beginning of Hershey's signature milk chocolate formula. This blend is then dried into chocolate crumb, a key intermediary unique to Hershey's process. The crumb is a dry, flaky mixture of milk solids, sugar, and chocolate liquor. It's stored in silos and later rehydrated with cocoa butter and emulsifiers during the refining stage. Creating crumb allows for a longer shelf life of the milk solids and helps develop the brand's distinctive, slightly tangy, malty flavor due to controlled milk fat breakdown during the crumb formation. Next comes refining, where the crumb and cocoa butter are combined and passed through a series of steel rollers. These rollers gradually reduce the particle size of sugar and cocoa to less than 30 microns. This fine reduction is critical for achieving the smooth mouthfeel of chocolate. If particles are too large, the texture becomes gritty. Too small, and it can feel pasty or dull on the tongue. The mixture exits this stage as a smooth, semi-fluid paste, ready for the next critical transformation, conching. In the conching process, the chocolate paste is agitated in large conche machines, steel troughs with granite or metal rollers that knead, heat, and aerate the chocolate continuously for up to 72 hours. This stage allows for further evaporation of unwanted volatile acids, the smoothing out of flavor edges, and the development of chocolate's rich, complex notes. The friction in conching also ensures the even distribution of cocoa butter, giving Hershey's chocolate its desirable melt-in-your-mouth quality. After conching, the chocolate is tempered. Tempering is the controlled crystallization of cocoa butter to ensure the chocolate sets with a glossy finish and satisfying snap. Hershey employs large-scale automated tempering units that carefully heat and cool the chocolate through a series of steps, bringing it down from around 45 degrees Celsius to 31 to 32 degrees Celsius for milk chocolate. This aligns the fat molecules into a stable crystalline structure, which gives the final bar its appealing texture and helps it resist bloom, where fat rises to the surface in white streaks. Once tempered, the liquid chocolate is piped into molds. The molding line consists of high-speed stations where molds are filled, vibrated to eliminate air bubbles, and chilled using cooled air or glycol-jacketed trays. For Hershey's iconic bars, molds are embossed with the brand's lettering and evenly segmented for snapping. The filled molds travel on a conveyor through a cooling tunnel that solidifies the chocolate completely within 8 to 12 minutes. Once cooled and hardened, the chocolate bars are demolded using a combination of vacuum systems and gentle mechanical actuators that pop them out without breakage. They move immediately into the packaging area, where a series of synchronized operations wrap, seal, label, and code each bar. Hershey's uses flow wrapping machinery that envelopes each bar in a foil and paper sleeve or film, depending on the product. The wrappers are printed with batch codes, best before dates, and product tracking identifiers. Every bar then undergoes quality control, which includes weight checks, X-ray scanning for foreign particles, and visual inspection by cameras that detect surface defects. Samples from each batch are taken to an on-site lab where texture, flavor, and microbiological safety are tested. If any irregularity is found, entire lots can be isolated thanks to the full traceability built into the production system. The packaged bars are then packed into cartons and stacked on pallets by robotic arms. The pallets are shrink-wrapped, barcoded, and sent to the distribution center. Hershey maintains temperature-controlled warehouses to ensure product stability, especially during summer months or shipments to warmer climates. Pallets are loaded into refrigerated or insulated trucks for distribution to stores across the country and abroad. What makes Hershey's chocolate truly unique isn't just the equipment or the ingredients, but the balance between automation and sensory control. While the machinery ensures consistency at massive volumes, sensory panels and chocolate experts continuously evaluate flavor, aroma, and texture to ensure every bar delivers the recognizable Hershey's profile. Even at the scale of hundreds of thousands of bars per day, this commitment to flavor accuracy and quality control is what maintains Hershey's reputation in the competitive world of confectionery. From cocoa bean to final bar, the industrial process behind Hershey's chocolate is a fascinating example of how tradition and technology merge. Every step, from roasting and grinding to conching and tempering, is carefully measured, controlled, and optimized. The result is a product that is not only nostalgic for many, but is also the outcome of over a century of engineering refinement and food science innovation. Cadbury's chocolate, with its unmistakably smooth texture and rich, creamy flavor, is one of the most beloved chocolate brands in the world. Its manufacturing process, while steeped in over a century of heritage, is executed today through a blend of tradition, advanced automation, and rigorous food science. At Cadbury's major production sites, such as the iconic Bournville factory in Birmingham, UK, every bar begins with careful ingredient sourcing and continues through precise steps involving milling, refining, conching, tempering, molding, and packaging. Across each stage, quality control, consistency, and signature taste are paramount. The first step in Cadbury's chocolate-making journey is the selection of raw ingredients. Cadbury's signature milk chocolate is made from a combination of full cream milk, sugar, cocoa butter, cocoa mass, and emulsifiers such as lecithin. Cadbury is known for using a relatively high percentage of milk solids compared to other mass-market chocolates, which contributes to its uniquely creamy flavor. For the UK and several international markets, Cadbury still uses fresh liquid milk rather than powdered or condensed forms. The milk is delivered daily to factories from nearby dairy farms, stored in chilled stainless steel silos, and constantly stirred to prevent separation. Meanwhile, cocoa beans, the fundamental ingredient in any chocolate, arrive at Cadbury's factories from West Africa, particularly Ghana, which provides a consistent, high-quality bean that is fermented and sun-dried prior to export. Upon arrival, these beans undergo detailed quality inspections before entering the factory system. They are cleaned thoroughly to remove foreign matter, dust, sticks, stones, or metal particles through a series of sieves, aspiration towers, and magnetic separators. Once clean, the beans are roasted. The roasting stage is one of the most vital steps for developing the chocolate's flavor. Cadbury uses hot air roasting techniques in rotating drum ovens or continuous flow systems, depending on the production volume. The temperature typically ranges from 120 to 150 degrees Celsius, and the roasting time can vary from 20 to 40 minutes. During roasting, the complex chemical reactions that form the Maillard compounds intensify the chocolate aroma and flavor, while also drying the beans to the ideal moisture level for further processing. After roasting, the beans are cooled and passed through winnowers, machines that crack them open and use air currents to separate the outer shells from the inner nibs. These cocoa nibs are rich in fat and flavor and form the base of both the cocoa mass and cocoa butter used in Cadbury products. The nibs are ground in heavy-duty mills to produce cocoa liquor, a thick, chocolatey paste made from pure nibs. Though liquid due to the heat generated during grinding, this liquor is made up of both cocoa solids and cocoa butter. At this point, the chocolate making process diverges depending on the final product. For Cadbury dairy milk and similar products, a crucial step involves combining the cocoa liquor with sugar and milk. Cadbury's defining feature is its use of fresh milk, which undergoes its own separate treatment. The milk is condensed with sugar in heated vacuum evaporators, producing a thick, rich liquid. This mixture is then blended with cocoa liquor and cocoa butter to create a homogeneous chocolate base. In traditional British-style chocolate making, as Cadbury does, this mixture is then dried into what is known as milk chocolate crumb. This dry crumb is unique to Cadbury and imparts a signature caramelized, malty undertone that distinguishes it from chocolates made with powdered milk or Swiss-style processing. The crumb is produced by drying the combined milk, sugar, and chocolate mixture in large drum dryers or vacuum drying systems, resulting in a sandy, dry granule that is easy to store and rehydrate in later stages. The crumb is stored in large silos until needed. When it's time to produce finished chocolate, it is remixed with additional cocoa butter. sometimes more cocoa liquor depending on the product, and emulsifiers like lecithin. This mixture is then passed through refining rollers, a series of 5 steel cylinders that reduce the particle size of the sugar and cocoa solids. The aim is to reach a uniform particle size of around 20 to 30 microns. This gives the chocolate a smooth texture without feeling gritty on the tongue. Particle size is verified using laser diffraction particle analysis systems to ensure consistency across every batch. Once refined, the chocolate enters the conching stage, named after the shell-like shape of early conching machines. This process involves mixing, shearing, and aerating the chocolate over several hours, anywhere from 4 to 24 hours, depending on the product. Conching removes volatile acids, unwanted moisture, and any rough flavor edges. Cadbury uses both traditional longitudinal conches and modern rotary conches, depending on the scale and specific chocolate formulation. During this time, the texture becomes silkier, and the flavor deepens and rounds out. Following conching, the chocolate is transferred to the tempering line, one of the most delicate and technically controlled stages in chocolate manufacturing. Tempering involves carefully cooling and reheating the chocolate to encourage the formation of stable cocoa butter crystals, which give chocolate its shiny appearance and clean snap. Improper tempering can result in chocolate bloom, a whitish, dull coating caused by fat separation. Cadbury's tempering machines operate in a closed-loop system, cycling chocolate through a precisely controlled thermal curve. Advanced digital sensors monitor viscosity, temperature, and flow characteristics to ensure optimal temper structure. Once tempered, the chocolate is ready for molding. Cadbury's high-speed molding lines pour the liquid chocolate into molds made of polycarbonate or food-grade stainless steel, depending on the product. The molds pass over vibration plates to eliminate air bubbles and ensure even distribution. The filled molds then travel through a cooling tunnel that gradually reduces their temperature to solidify the chocolate without causing stress fractures. This ensures a uniform, glossy appearance and the correct snap when broken. Demolding is performed using vacuum lifters or gentle mechanical knockers, depending on the mold shape. For filled products like Cadbury cream eggs or caramel bars, the process includes an additional step. Shell molds are created by partially filling and spinning molds to create a cavity, which is then filled with the flavored fondant or caramel using precision depositor heads. These centers are allowed to partially set before a chocolate-based layer is applied, and the molds are fully sealed, then cooled and demolded just like solid bars. Once the chocolates are demolded, they move directly to the packaging lines. Here, automated machinery wraps individual bars in foil and branded sleeves or flow wraps them in film. The packaging materials are printed with batch codes, expiry dates, and traceability data. Optical scanners and X-ray systems perform real-time quality checks, looking for surface imperfections, air gaps, or foreign matter. Any product not meeting the strict standards is ejected from the line automatically. The wrapped bars are then grouped into cartons or multi-packs, which are robotically packed into shipping cases. These cases are barcoded, palletized by robotic arms, and shrink-wrapped for shipping. Pallets are stored in temperature-controlled distribution centers until they are shipped out to retailers. The entire inventory system is managed using enterprise-grade software that tracks each chocolate bar from production to warehouse to store shelf. What distinguishes Cadbury's industrial chocolate production from others isn't just its recipe, but its integration of craftsmanship and automation. Despite being a global brand, producing millions of bars per week, Cadbury maintains tight control over flavor, texture, and appearance through every stage, from the exact ratio of milk solids to the particle size in refining and the thermal curves of tempering. Every sensor, every conveyor, and every batch record plays a part in delivering a final product that's as familiar as it is meticulously engineered. Even sustainability is built into the process. Cadbury's factories are gradually moving toward carbon neutrality, with newer systems recovering heat from roasting for use in conching, and solar panels offsetting daytime energy use. Additionally, cocoa is increasingly sourced through the Cocoa Life program, which promotes fair trade, farm productivity, and community development in West Africa. In the end, every Cadbury Dairy Milk bar is a result of over a century of refinement, rooted in British chocolate-making tradition, but carried out in some of the most sophisticated food production environments in the world. From fresh milk and raw cocoa to the purple-wrapped bar, every step reflects a balance of nostalgia and precision, heritage and innovation. Mars chocolate bars, instantly recognizable by their dark chocolate coating, nougat core, and caramel layer, are manufactured through one of the most highly refined industrial processes in the global confectionery world. While the experience of biting into a Mars bar feels simple and indulgent, the behind-the-scenes production is anything but. It requires precision control of temperatures, flow rates, ingredient ratios, and mechanical handling, executed across multiple synchronized systems in high-speed, high-volume manufacturing plants. The entire process, from raw ingredient reception to molded bars in wrapped form, is designed for repeatability, safety, and sensory consistency, ensuring every Mars bar tastes identical to the last, whether it's made in the UK, the US, or elsewhere. It all begins with sourcing the core components: cocoa, sugar, milk, glucose syrup, and fats. Mars procures its cocoa through long-term supply contracts with farms across West Africa, where cocoa beans are fermented and dried on site before being shipped to processing facilities. Sugar is sourced from sugar beets or cane, depending on the regional plant. The milk component often comes in the form of milk powder or condensed milk, chosen for stability and easier integration into industrial formulations. Mars also uses specialty fats, vegetable oils, and cocoa butter blends for different parts of the bar to achieve specific textures and melting properties. Each of these ingredients is subjected to stringent quality control upon arrival. Cocoa powder is tested for fat content, microbial load, and flavor integrity. Milk powder is checked for protein and moisture levels. Sugars are screened for crystal size and cleanliness. Once cleared, they are transferred to bulk storage systems that feed directly into the production lines through enclosed, pressurized delivery tubes to minimize contamination. The first component to be produced on the line is the nougat base, which forms the soft but chewy core of a Mars bar. Nougat for Mars bars isn't the traditional egg white variety seen in artisanal confectionery, but a carefully engineered formula based on a whipped blend of sugar, glucose syrup, hydrolyzed soy protein, and milk powder. The dry and liquid ingredients are first mixed in large batch tanks equipped with high shear mixers. The mixture is heated to approximately 120 degrees Celsius to dissolve all solids and activate syrup structure, then cooled rapidly as it enters the aeration system. Aeration is critical. The hot syrup is whipped with nitrogen gas, chosen over air or CO2 because it's inert and maintains longer shelf stability. This whipping happens in high-capacity continuous mixers equipped with rotor-stator assemblies that shear and expand the mass into a light, foamy structure. The density is controlled down to the gram per cubic centimeter using inline flow meters and laser sensors. The freshly aerated nougat is extruded onto a cooling belt made of food-grade stainless steel or polyethylene-coated fabric. The belt runs beneath a cooling tunnel where chilled air brings the nougat's temperature down to a manageable level for further layering. At this stage, it appears as an endless beige ribbon, roughly the width and height of a Mars bar. Next comes the caramel layer, which is produced in parallel and deposited directly onto the top surface of the nougat ribbon. Caramel in Mars bars is made from a cooked mixture of glucose syrup, sugar, dairy solids and fats, brought to a high boil under vacuum to reach the right viscosity and prevent crystallization. Caramel cookers, jacketed stainless steel kettles fitted with vacuum systems, ensure that the water content is carefully reduced without burning the sugars or degrading the milk proteins. Once cooked, the caramel is pumped into a spread depositor, a mechanism that lays down a smooth, even layer of caramel over the moving nougat sheet. The temperature of the caramel during application is closely monitored, usually around 40 to 45 degrees Celsius, to maintain spreadability without melting the nougat underneath. As the composite sheet of nougat and caramel moves along the line, it enters a laminar cooling tunnel, where chilled air slowly brings both layers down to cutting temperature. This ensures that the final bar will maintain its shape during slicing. After exiting the cooling tunnel, the layered slab is conveyed to a guillotine cutter, an automated, high-speed mechanical blade that slices the continuous sheet into individual bar-sized pieces. The cutter is synchronized with the speed of the conveyor, allowing it to produce thousands of consistent cuts per hour without crushing or dragging the layers. Optical sensors track the integrity and alignment of each cut, automatically rejecting any malformed pieces before they move to the next phase. The sliced centers are now ready for enrobing in chocolate. Each nougat caramel piece is placed onto the in-feed conveyor of a high-speed chocolate enrober. This machine pumps liquid chocolate, produced from a blend of cocoa liquor, cocoa butter, sugar, milk powder, and emulsifiers, over the bar in a curtain-like flow. The bottoms are coated first by passing over a shallow chocolate bath. Then the rest is coated from the top and sides via falling curtains of tempered chocolate. The chocolate used in Mars bars is carefully tempered beforehand. Tempering is the process of heating, cooling, and reheating chocolate to create a uniform fat crystal structure, giving the coating its shine, firmness, and resistance to bloom. Mars uses fully automated tempering units that precisely control chocolate temperature to within fractions of a degree, cycling through heating coils and chilled plates in sequence before delivery to the enrober. As each piece exits the enrober, it passes over a vibration plate that shakes off excess chocolate and ensures even coverage. Some lines use air knives, streams of compressed air directed at specific angles, to remove chocolate buildup from the sides or base of the bar. The freshly coated bars then enter a cooling tunnel that runs for 15 to 20 meters, gradually reducing their temperature in controlled stages to prevent cracking or moisture condensation. These tunnels use chilled, dehumidified air at around 8 to 12 degrees Celsius. Once the chocolate has fully set, the bars proceed to the wrapping line. Here, high-speed flow wrapping machines encase each bar in metallized polypropylene film, heat sealing both ends and the back. Wrapping machines include inline printers that apply the best before date, batch number, and factory code directly onto the film. Optical scanners check each wrapper for print clarity, alignment, and seal integrity. Any bar with misaligned film or poor sealing is ejected from the line by pneumatic arms into a separate rework bin. Wrapped bars are counted and grouped into cartons, which are then sealed, labeled, and moved to robotic palletizing systems. Robots arrange cartons in predefined patterns onto pallets based on flavor, size, and shipping destination. Each pallet is barcoded and logged into Mars ERP system for real-time traceability. Pallets are stored in climate-controlled warehouses maintained at 18 to 20 degrees Celsius and under 50% relative humidity to preserve the chocolate's shelf life and prevent bloom or fat migration. The entire production line is monitored via SCADA systems, software platforms that oversee machine parameters, product flow, and quality metrics in real time. Operators at control stations can view temperature logs, flow rates, equipment performance, and reject rates. If a sensor detects even a slight deviation, like a variation in caramel viscosity or enrobing temperature. Alerts are issued and adjustments are made immediately to avoid wasting product or compromising quality. The base of the Dubai chocolate bar, its foundation both in flavor and in structure, is the chocolate itself. For these premium, high-gloss, visually striking bars, the chocolate used isn't just any standard compound chocolate. Factories producing luxury Dubai-style chocolates source couverture chocolate, which contains a high percentage of cocoa butter and is specifically designed for tempering and molding. These chocolates often include blends of West African, Ecuadorian, or Madagascar origin beans, selected for their rich cocoa flavor, smooth melt profile, and balanced bitterness. Suppliers provide the chocolate in tempered blocks or pistoles, coin-sized discs, which are stored in climate-controlled rooms to prevent bloom and preserve integrity before processing. At the start of the shift, blocks or discs of chocolate are moved from storage into the production room. These rooms are maintained at specific ambient conditions, typically around 18 degrees Celsius with 50% relative humidity, to allow tempering and molding without risk of streaking, sweating, or air bubble formation. Chocolatiers, or automated systems, begin by pre-melting the chocolate using high-capacity melters. These are stainless steel, jacketed vats equipped with controlled heating elements and agitators that slowly bring the chocolate to its first melt point, typically between 45 to 50 degrees Celsius. This stage liquefies the chocolate but destroys the ideal crystalline structure of the cocoa butter, which must be reformed through tempering. Tempering is where the magic of Dubai chocolate truly begins. Factories use continuous tempering machines that heat, cool, and reheat the chocolate through very precise temperature curves, raising it to melt all crystals, cooling to encourage type 5 crystal formation, and reheating slightly to remove unstable crystals. For dark chocolate, the temperature typically moves from 45 degrees Celsius down to 27 degrees Celsius, then back up to 31 to 32 degrees Celsius. For milk and white chocolates, the curve is slightly lower. This tempering process ensures the final bars will be glossy, firm, and have the perfect snap. Meanwhile, molds are being prepared. These aren't generic molds, but custom-engineered polycarbonate bar molds, often with deep cavities to accommodate fillings like pistachio cream and crispy kataifi layers. The molds are stored in warming cabinets to match room temperature and prevent condensation from forming when they come in contact with tempered chocolate. Some manufacturers polish the molds manually using cotton cloths to remove even microscopic dust, ensuring a mirror-smooth chocolate finish. The tempered chocolate is deposited into the molds using precision dosing heads. These automated nozzles fill each cavity with a controlled volume of chocolate, usually just enough to coat the bottom and sides without overfilling. The molds then move along a vibration table, where subtle vibrations remove trapped air bubbles and help the chocolate settle into every edge and corner. This step is critical, not just for appearance, but also to prevent structural weak points that could crack or collapse during demolding. Once the initial shell layer is in place, the molds are inverted and pass through a continuous spinner or a centrifugal molding carousel. This equipment allows excess chocolate to spin out of the center while leaving a consistent coating on the mold walls. What's left is a perfect hollow shell, cooled slightly using a refrigerated tunnel to harden the chocolate and lock it in place. While the shells are cooling, the filling stations prepare the interior layers. The signature filling in Dubai chocolate bars is pistachio cream, often made in-house for quality control. Shelled pistachios are first dry roasted at 130 to 150 degrees Celsius for about 10 minutes to intensify their flavor. They are then cooled and transferred into high shear grinders that pulverize the nuts into a fine paste. The pistachio paste is blended with white chocolate, milk solids, a small amount of cocoa butter, and sometimes tahini or cream powder to achieve the creamy, slightly earthy, subtly sweet taste that defines the filling. Emulsifiers such as lecithin may be added to maintain a smooth texture over time and to prevent oil separation during storage. The resulting pistachio cream is then stored in stainless steel hoppers, held at about 30 degrees Celsius to keep it fluid enough for piping without damaging the chocolate shell upon contact. Before filling, technicians or robotic gantry systems insert a dosing nozzle into each chocolate shell and carefully deposit a measured amount of pistachio cream, usually leaving just enough space to accommodate the crisp layer above. That crispy layer often comes from kataifi, a traditional Middle Eastern shredded pastry. The kataifi is first baked on separate lines until golden and dry, then broken into small flakes. These flakes are carefully mixed with a binding agent, typically cocoa butter or a touch of caramelized sugar syrup, to allow them to adhere slightly and remain crunchy. This mixture is sprinkled or pressed gently over the pistachio cream layer inside each mold. Some factories automate this using vacuum-assisted dosing heads that drop a consistent portion into each mold cavity. Once the layers are complete, a final layer of tempered chocolate is applied to seal the mold. This is done using an enrobing or capping station that spreads chocolate smoothly across the mold's top surface and ensures full encapsulation. The molds are then vibrated again briefly and sent through a second cooling tunnel. Here, chilled air at around 10 to 12 degrees Celsius circulates gently for up to 15 minutes to allow complete crystallization of the chocolate. After cooling, the molds exit onto the demolding line. Here, they are turned upside down and flexed slightly, either manually or via robotic arms. Properly tempered chocolate contracts just enough to release cleanly from the polycarbonate surface without cracking or dulling. The bars fall onto padded conveyors or vacuum grip trays, ready for inspection. Once the molded Dubai chocolate bars are demolded and cooled, the production process transitions into the most visually striking and luxurious stage, finishing. This is where the bars are transformed from a technical product of industrial chocolate molding into a boutique, premium confection. With Dubai's global reputation for opulence, excess, and high-end presentation, it's no surprise that even in chocolate manufacturing, aesthetics play a central role. This part of the factory is designed less like a utilitarian processing zone and more like a controlled artistic studio where specialized machines and skilled staff bring out the final appearance of each bar with precision, uniformity, and flair. The freshly demolded bars are first visually inspected under high CRI LED lighting panels. These lights expose any imperfections that may have occurred during molding: air pockets, dull finishes, cracks, or slight deformities. Bars that don't meet visual criteria are pulled from the line and either reprocessed, if still fresh, or sent to controlled scrap and recycling channels, where chocolate is melted down and retempered for reuse. This immediate sorting ensures that only flawless units proceed to decoration. The next step for many of these signature Dubai chocolate bars is gilding. Edible gold leaf, usually 23 karat and certified food safe, is applied to the surface of the chocolate using specialized vacuum-assisted applicators. The machines can pick up extremely delicate gold leaf squares using a static charge or microsuction nozzle and gently place them onto the bar in predetermined areas. In smaller production runs, trained chocolatiers perform this manually using tweezers and food-grade brushes. The gold leaf is applied not just for aesthetics, but to signal luxury and exclusivity, and its placement is often symmetrical and consistent across units to maintain brand uniformity. Alongside gold leaf, some chocolate bars are airbrushed with colored cocoa butter using precision spray booths. These booths resemble scaled-down automotive spray rooms, complete with exhaust ventilation, stainless steel walls, and particle capture filters. Colored cocoa butter, made by blending natural pigments into tempered cocoa butter, is warmed to the correct temperature, around 32 degrees Celsius for milk chocolate compatible tones. and loaded into gravity-fed spray guns or robotic airbrush nozzles. Bars are lined up on a rotating turntable or conveyor and sprayed with gradients, accents, or patterns. Popular color schemes include metallic bronze, emerald green, ruby red, or deep purple, each one matched to the flavor profile or seasonal branding of the product. If a layered or textured finish is desired, chocolate or ganache drizzles are applied next. These are executed with temperature-controlled piping heads mounted on robotic arms. The arms follow programmed paths based on CAD models of the bar's surface, ensuring that each drizzle is consistent in thickness and placement. These drizzles can be solid-colored or contain inclusions like crushed pistachio, rose petal powder, or saffron threads. Timing and ambient temperature are tightly regulated to prevent these delicate decorative layers from smudging or sweating. After decoration, the bars undergo a final cooling cycle, not for structural reasons, but to stabilize surface temperatures and prevent condensation or bloom once the bars are placed into packaging. This is especially critical in the Middle East, where ambient humidity and temperature fluctuations can damage the surface sheen of premium chocolate. The cooling tunnel at this stage is not as aggressive as earlier ones. It's more of a conditioning zone, holding bars at 18 degrees Celsius with controlled humidity around 45 to 50%. Once the bars are stabilized, they proceed to the packaging line. This area is often divided into multiple stations, depending on the type of packaging required. For most Dubai-style luxury bars, packaging involves several layers: a protective inner sleeve, an airtight barrier wrapper, and an external rigid box. First, the chocolate bar is slid into a clear or gold-accented plastic or mylar sleeve, sealed using ultrasonic or heat-sealing jaws to prevent oxygen exposure. This barrier packaging preserves aroma and prevents flavor migration or moisture penetration. Next comes the presentation stage. The bars are placed by robotic pick-and-place arms into rigid paperboard or tin boxes lined with velvet, foam, or satin finish inserts. These boxes are embossed, foil stamped, or UV printed with brand insignia, flavor indicators, and production codes. Depending on the SKU, a magnetic flap or ribbon-tied closure is used to elevate the unboxing experience. For ultra-premium editions, each bar may come with a printed card describing its flavor profile, production number, or recommended consumption temperature. Every packaged bar passes through final QA scanning stations where barcode, label placement, box orientation, and seal integrity are checked using high-speed vision systems. These cameras detect even minute misalignments or defects in outer packaging and divert non-compliant products for manual review. The accepted boxes are grouped into cartons by flavor and SKU, palletized, and sent to a temperature-controlled warehouse section where final shipment staging takes place. Warehouse storage for Dubai chocolate bars isn't just about space, it's about microclimate management. Chocolate, especially when decorated with cocoa butter colorants or metallic finishes, is highly sensitive to light, temperature, and humidity. The warehouse rooms are often subdivided into climate zones, tailored to specific packaging formats. Bars with thinner walls or heat-sensitive decorations are stored at slightly lower temperatures. Light exposure is minimized with motion-activated LED lighting, and all pallets are labeled with humidity-tolerant RFID tags that allow real-time temperature tracking during storage and transportation. Shipping protocols are equally meticulous. For domestic UAE distribution, insulated vehicles with air-cooled compartments maintain optimal transport temperatures. For export shipments, especially to countries with varying climates, the bars are packaged with phase-change gel packs or packed into refrigerated containers. Shipment boxes include thermal sensors and tamper-evident seals, ensuring that the end customer receives a product as flawless as when it left the factory. Throughout all of this, quality control teams operate in parallel, sampling units from each batch at every stage. They test not only for appearance and packaging, but for internal parameters: fat bloom stability, water activity, filling pH, shelf life projection, and chocolate viscosity retention. Microbiological samples are sent to internal labs or third-party facilities to validate that storage, filling, and decoration processes meet international food safety standards. With the physical production of Dubai chocolate bars now completed, from tempering to molding, from filling to gilding, and finally to packaging, the factory's work turns to a more nuanced, ongoing responsibility: innovation. While consistency is essential to any luxury confection, what truly defines Dubai's chocolate culture is its willingness to blend elegance, excess, and regional identity with bold reinvention. And so, even after one product line has been finalized and stored, the wheels of creation keep turning. Chocolate in Dubai is not just a sweet, it's a symbol of fusion, indulgence, and modern sophistication. Inside the R&D suites of Dubai's leading chocolate factories, where cleanroom-grade workstations meet experimental kitchens, chocolatiers and food scientists collaborate on the next evolution of flavor, texture, and visual design. These spaces are a world apart from the high-volume production halls, quieter, more intimate, and filled with carefully labeled jars of dried flower petals, roasted nuts, rare spices, fruit leathers, and aromatic oils. The air smells like roasted cocoa, cardamom, orange zest, and rose. Here, every square centimeter of a chocolate bar is considered for its potential to convey both craftsmanship and cultural depth. It begins with the ingredients. To keep their offerings ahead of international trends, Dubai's chocolate manufacturers often source from premium suppliers across the globe. Pistachios might come from Bronte in Sicily, known for their intense flavor and deep green hue. Saffron may be flown in from Mashhad, Iran, packaged strand by strand in glass tubes. Sea salt is sometimes imported from Guérande, France, while dried fruits are infused with natural rosewater or hibiscus before being included in limited edition bars. This obsession with quality doesn't stop at sourcing. The chocolate base itself is often reformulated for experimental bars, sometimes using ultra-dark, single-origin chocolate from Madagascar with a 72% cocoa content, or ivory white couverture with additional cocoa butter for an ultra-soft melt. Food technologists work with these ingredients in small test batches, melting, blending, tempering, and setting, always using laboratory-grade scales and digital thermometers to maintain chemical accuracy. For filled bars, viscosity of the ganache or cream filling is constantly monitored. Too runny, and it will collapse the shell. Too thick, and it won't distribute properly during piping. Once a new concept has been mocked up, it enters the tasting phase. In Dubai, tasting panels often include not only technical staff, but chefs, branding executives, and even invited guests from high-end hotels and patisseries. These panels assess more than just taste. They consider the chocolate's melt curve, the harmony of sweet, bitter, and umami notes, how the aroma develops on the palate, and whether the textures unfold as intended. Soft cream, followed by crunchy kataifi, followed by a firm snap of tempered chocolate. Any design that passes this rigorous screening may be pushed forward into limited-scale test production. In this pilot phase, all production steps are replicated exactly as they would be in the full-scale plant, but with volumes as small as 100 to 500 units. This stage isn't just about scaling the recipe, it's about validating that the filling doesn't collapse during shipping, that colored cocoa butter doesn't rub off inside the packaging, and that the product can maintain its shelf stability across 45 days in various climates. Sometimes, the pilot batch becomes a seasonal or VIP-only product. Dubai chocolate brands frequently collaborate with luxury hotels, fashion houses, or jewelers to release small runs of co-branded chocolate bars. These may come in custom boxes lined with suede or velvet, with hand-tied ribbons, foil-stamped logos, and embossed certificates of authenticity. It's not unusual for such bars to be served exclusively in first-class airline cabins or to be included as part of a luxury event's welcome package. What's unique about Dubai's chocolate industry is how seriously it treats the visual element. Bars are not just flavored, they are composed. Swirls of color, embossed patterns, layers of inclusions. Each design is meant to photograph well, unbox dramatically, and hold visual appeal under both natural and artificial lighting. This makes sense in a city where luxury and visual branding are closely intertwined. As a result, the design team in the chocolate factory often includes not only food stylists, but graphic designers and packaging engineers who ensure the chocolate looks as extraordinary as it tastes. Technology plays a growing role in supporting this artistic process. 3D printing has begun to infiltrate chocolate design in Dubai's more advanced factories. Prototypes for new molds are created using CAD software, then printed using food-safe polymer or silicone. This allows for complex, curved, or asymmetrical mold shapes to be tested without expensive tooling. Once approved, the designs can be machined into production-ready polycarbonate molds or transferred to injection molders for large batch production. Another rising trend in Dubai chocolate manufacturing is the use of modular assembly. Rather than pouring each bar in a single continuous line, some premium chocolate bars are assembled in components: shell, filling, topping, seal, and decorative layer. This modular approach allows for faster customization and easier experimentation because only one layer needs to change at a time during the design iteration phase. For instance, a pistachio bar might be converted into a rosewater version simply by swapping the flavored cream in the second step of the assembly line. Automation continues to support consistency but is often paired with strategic human intervention. For example, while the molding, depositing, and sealing stages may be fully automated, finishing stations, where gold flakes are applied or freeze-dried raspberry slices are manually positioned, still rely on trained artisans. This hybrid production model enables the factory to maintain scale while preserving the handmade aesthetic that luxury customers associate with authenticity and care. Throughout all these innovations, strict hygiene and safety standards are maintained. Clean rooms for production are equipped with air filtration, temperature control, and antimicrobial flooring. Workers wear specialized uniforms, and hands-free wash stations are positioned at every entry. For allergen control, dedicated lines are established for products containing nuts, dairy, or sesame, with full equipment sanitization between runs. Each batch is logged with a digital traceability tag that links every ingredient and production step to a central database, ensuring total recall capability if needed. As the innovation cycle continues, customer feedback becomes another input. Dubai's chocolate companies often collect feedback not just through retailers, but via luxury hotel concierges, fine dining establishments, and curated tasting events. QR codes inside packaging lead to private digital feedback portals, where customers can rate individual elements: aroma, melt, sweetness, packaging, mouthfeel, and overall impression. This data is reviewed by product teams and occasionally even presented during board-level meetings to shape future strategy. And as international interest grows, Dubai chocolate makers are looking to expand their reach. Export strategies include partnering with duty-free retailers, developing cold chain distribution protocols for overseas shipping, and adapting packaging to meet European and North American labeling laws. Still, the core identity remains rooted in Dubai's unique cultural aesthetic, where East meets West and tradition fuses with luxury modernism. As Dubai's chocolate industry matures and gains global recognition, the focus is no longer solely on aesthetics, flavor, and luxury appeal, it's also shifting towards sustainability, technological integration, and consumer engagement. Factories that once prioritized opulence above all are now aligning with international standards in environmental responsibility, ethical sourcing, and digital transparency, all while preserving the essence of what makes Dubai's chocolate so distinct. This final phase in the factory's operation reveals how innovation and conscience now work hand in hand behind the scenes. One of the most immediate challenges facing Dubai's chocolate factories is packaging. While traditional high-end packaging, velvet-lined boxes, foil embossing, and ornate structural design conveys luxury, it often falls short in sustainability. Many components, especially multi-layer laminates, magnetic closures, and plastic films, are difficult to recycle. To solve this, Dubai's leading chocolatiers are investing in eco-luxury packaging, biodegradable film wraps made from cellulose, FSC-certified rigid cartons, and plant-based inks for printing. These materials are carefully selected not just for their environmental performance, but for how they perform in Dubai's climate, where heat and humidity pose a threat to both packaging integrity and chocolate shelf life. To maintain elegance while reducing environmental load, factories have developed dual packaging streams, one for export, which may include insulation and cold chain protection, and one for local retail, simpler, recyclable formats with reusable inserts. Specialized packaging engineers model airflow, light exposure, and condensation risk within each box, ensuring that even the most minimalistic package still protects the chocolate through its full shelf life. Many factories also use RFID tags or QR-coded stickers that provide batch traceability while replacing plastic promotional inserts or brochures. On the ingredient side, ethical sourcing is a major point of transformation. Dubai's high-end chocolate producers, particularly those working with couverture or single-origin blends, are investing in direct trade relationships with farms in Ecuador, Ghana, Madagascar, and Venezuela. Rather than buying anonymous commodity cocoa, they work with micro-cooperatives and certified farms that provide full transparency over labor practices, land management, and cocoa fermentation methods. These beans are traceable down to the hectare. Some suppliers even include QR codes on each sack, allowing Dubai's buyers to view GPS data, fermentation logs, and harvest dates before accepting shipment. Once the beans are roasted, ground, and transformed into couverture by suppliers, or occasionally on-site in Dubai's bean-to-bar micro facilities, the factories maintain this chain of transparency using blockchain platforms. Every step, from the pistachios harvested in Bronte to the saffron threads weighed in Tehran, is logged digitally. These platforms allow high-end retailers, distributors, and even consumers to access the full journey of each bar, complete with certifications, batch data, and sustainability impact reports. This isn't just for marketing, it's becoming a standard requirement for selling in premium retailers across Europe and Asia, where food transparency is increasingly mandated. Waste management is another area of rapid progress. Chocolate production naturally generates byproducts, offcuts, failed batches, excess fillings, packaging trim. In the past, much of this would be discarded or relegated to animal feed. Today, Dubai's factories operate circular systems that recover chocolate scrap and retemper it under strict rework protocols. Food-grade chocolate that was rejected due to cosmetic flaws is remelted, retempered, and reformed into couverture blocks for non-decorative uses. Fillings that pass microbiological standards are used in filled truffles or mixed into baked goods at partner bakeries. Even the gold leaf, an iconic but expensive element, is carefully tracked. Automation now controls the application of each flake, minimizing overuse, and any that misses the chocolate surface is vacuum collected, filtered, and returned to a recycling crucible for future use. This precision has helped reduce material loss by over 30% in some facilities, saving cost and minimizing excess use of non-renewable resources. Energy consumption is another core concern, particularly in Dubai's hot desert climate, where cooling systems must run year-round to preserve chocolate texture and prevent blooming. Factories have upgraded their infrastructure with double-insulated production rooms, solar-assisted chillers, and motion-activated cooling systems. Rooftop solar arrays now power not only office and lighting systems, but also support the energy needs of non-critical machinery like conveyors, label printers, and data terminals. Factory roofs are often painted with heat-reflective coatings to reduce ambient load, and dehumidifiers now use heat recovery technology to pre-warm cleaning water or process inputs. Water use has also been targeted for reduction. While chocolate production does not use water directly in the bar making process, cleaning and sanitation consume substantial volumes. Dubai factories now implement closed-loop CIP clean-in-place systems that clean pipework, tanks, and melters using minimal water volumes and reclaim rinse water for grey water processes like floor washing. Reverse osmosis filtration systems further reduce water waste, and sanitation logs are tied to efficiency benchmarks that incentivize teams to use only what is necessary without compromising hygiene. Technological innovation continues to reshape how the factory operates at every level. AI now plays a significant role in sensory profiling. Special tasting booths are outfitted with aroma sensors and machine learning software that maps the volatile compounds released by each chocolate bar during a controlled melt. This data is then compared to a library of target flavor profiles, helping QA teams identify any deviations in aroma balance before the bars are even wrapped. This ensures that every Dubai chocolate bar not only looks premium, but smells and tastes exactly as intended. Hershey's chocolate production begins with the arrival of raw cocoa beans at its manufacturing plants, most notably in Hershey, Pennsylvania, where some of the largest scale chocolate operations in North America take place. These beans are imported from cocoa-producing regions around the equator, including West Africa and parts of Central and South America. Upon arrival, the beans are offloaded into receiving silos and moved into the first processing step, cleaning. Powerful vibrating screens, aspirators, and magnetic separators remove debris, stones, twigs, dust, and any metallic fragments that may have entered the shipment during transit. Following cleaning, the cocoa beans are fed into Hershey's proprietary roasting system. The roasting process is designed not just to sterilize the beans, but to precisely control flavor development. The machines are capable of adjusting roast temperature, humidity, and dwell time based on the origin, size, and moisture content of each batch. Beans are typically roasted at temperatures ranging from 120 to 160 degrees Celsius. This is where the characteristic chocolate aroma begins to develop, as volatile compounds are released and the Maillard reaction activates, producing hundreds of unique flavor notes that define Hershey's mild, sweet chocolate style. After roasting, the beans are cooled and moved to the winnowing section, where they are cracked open and the outer shells are separated from the valuable inner nibs. Winnowing is accomplished using a combination of mechanical cracking and airflow separation. The shells, now removed, are often collected and repurposed as agricultural mulch or biomass fuel. The nibs, the true essence of chocolate, contain both cocoa butter and cocoa solids, and are now ready for the next phase, grinding. The nibs are fed into high-capacity industrial grinding mills, where intense mechanical shear forces break down the cellular structure and release the natural cocoa butter, forming a dense, fluid paste known as chocolate liquor. Despite its name, chocolate liquor contains no alcohol. This liquor is a pure, unsweetened, dark brown substance composed entirely of finely ground cocoa particles, suspended in cocoa butter. From here, the liquor may go into temporary holding tanks or be immediately sent to blending tanks, depending on product demand. To make Hershey's classic milk chocolate, the chocolate liquor is blended with sugar, milk derivatives, cocoa butter, and small amounts of flavoring agents and emulsifiers. What makes Hershey's process unique is its use of fresh milk, originally pioneered by Milton Hershey himself, which is condensed and cooked on site. This milk is blended with sugar and chocolate liquor to form a slurry, which is then dried into what's known as milk crumb. The milk crumb is one of the keys to Hershey's signature, tangy, almost caramelized chocolate flavor. Unlike many European chocolate makers who use dry milk powders, Hershey's milk crumb production adds distinctive cooked dairy notes that have become synonymous with the brand's taste. The crumb mixture is then blended with additional chocolate liquor and cocoa butter in massive mixers to create a semi-fluid chocolate paste. This paste now contains all of the major components of Hershey's chocolate: milk solids, sugar, cocoa mass, and cocoa butter. However, it still needs to be refined to achieve the ultra-smooth texture that consumers expect. This refinement is achieved using a 5-roll mill, a piece of precision equipment where the chocolate paste is passed through a series of steel rollers that reduce particle size down to around 15 to 20 microns, small enough that the human tongue can no longer detect individual sugar or cocoa particles. Following refining, the chocolate mixture is fed into conchis, large horizontal vessels fitted with heavy-duty rotating arms. Conching is both a mechanical and thermal process in which chocolate is kneaded and aerated for several hours at controlled temperatures. During this stage, volatile acids are evaporated, off flavors are reduced, and cocoa solids become fully coated in cocoa butter, resulting in a more uniform flavor and mouthfeel. Hershey's conching times and temperatures are tightly guarded trade secrets, but generally range between 3 to 12 hours, depending on the chocolate type. Once conching is complete, emulsifiers like soy lecithin or PGPR may be added to improve flow characteristics and ensure the chocolate performs consistently during molding and enrobing. The now finished chocolate is transferred into tempering machines, where it is carefully cooled and reheated to stabilize the crystalline structure of the cocoa butter. Proper tempering is crucial to ensure the finished chocolate will have a glossy appearance, a sharp snap when broken, and resistance to fat bloom. Tempered chocolate is then routed to forming lines. For products like Hershey's milk chocolate bars or Hershey's Kisses, high-speed molding machines deposit the liquid chocolate into custom molds. These molds are vibrated to eliminate air bubbles and achieve uniform density before passing through long cooling tunnels. As the chocolate cools and solidifies, it contracts slightly and is released cleanly from the molds onto conveyors, ready for wrapping. Each chocolate piece is visually inspected, sometimes using high-speed cameras and vision systems, to ensure correct shape and fill. Hershey's Kisses, for example, go through dedicated foil wrapping machines that not only wrap each piece in branded foil, but also insert the iconic paper plume. Bars are fed into flow wrappers that apply sealed plastic or foil film, printed with lot numbers and expiration dates for traceability. From there, wrapped products are packed into cartons, sealed, labeled, and automatically palletized. Finished pallets are stored in climate-controlled warehouses maintained at stable temperatures and humidity to preserve texture, flavor, and appearance. Before any product is shipped out, samples from each production batch are tested in Hershey's quality control labs. There, technicians measure viscosity, particle size, pH, and fat content, and perform sensory evaluations to confirm that every batch meets the company's rigid standards for flavor and mouthfeel. Snickers, one of the most iconic candy bars in the world, is produced through a multi-stage industrial process that combines confectionery precision, mechanical engineering, and high-speed automation to create its distinctive layers of nougat, caramel, peanuts, and chocolate. Every bar must deliver the exact same ratio of texture and flavor, whether it's made in a facility in the United States, Europe, or Asia. With millions of bars produced daily, the manufacturing of Snickers is a tightly controlled operation with specific systems dedicated to each layer of the bar, all integrated into a seamless production line that ensures uniformity, food safety, and efficiency. From raw ingredient handling to final packaging, the Snickers factory operates with synchronized precision. Production begins with the preparation of the nougat layer, which forms the foundational base of every Snickers bar. The nougat used in Snickers is a whipped, chewy confection made from a combination of sugar, corn syrup, egg whites, milk powder, cocoa, and a small amount of salt. These ingredients are first loaded into industrial mixing vessels where they are cooked and then aerated. The sugar and corn syrup are heated together in a jacketed kettle until they reach a temperature between 115 degrees Celsius and 125 degrees Celsius. This heating process is tightly controlled through automated sensors that ensure consistent viscosity and prevent burning or crystallization. Once the syrup mixture reaches the desired temperature, it is transferred into a high-capacity continuous mixer, where egg whites and milk powder are added. Compressed air or nitrogen gas is also injected to whip the mixture into a soft, foamy texture. This aeration step is critical. It gives the nougat its characteristic lightness and chewiness. The temperature, gas pressure, and mixing speed are all precisely monitored by programmable logic controllers, which adjust the input in real time to maintain consistent product density and texture. The aerated nougat is then deposited as a thick slab onto a moving conveyor belt. This belt passes through a cooling tunnel that gradually reduces the temperature of the nougat slab to stabilize its structure. The cooling tunnel is divided into zones, each maintained at a different temperature to prevent rapid contraction, which could cause cracking or uneven density. Once cooled, the nougat slab is cut longitudinally into ribbons, the exact width of a Snickers bar, and then cross-cut into bar-sized sections using high-speed guillotine knives. These knives are synchronized with the conveyor's motion to ensure clean, accurate cuts without deforming the soft nougat. Next comes the caramel layer. The caramel used in Snickers is thick and elastic, designed to stretch but not melt under room temperature. It is made from a cooked blend of glucose syrup, sugar, milk solids, butterfat, and a carefully calibrated emulsifier. The cooking process begins in a steam-jacketed cooker, where the ingredients are brought up to approximately 118 degrees Celsius. The precise cooking temperature ensures the right balance between chewiness and flow. Overcooked caramel would become brittle, while undercooked caramel could seep through the nougat or ooze during packaging. Once cooked, the caramel is pumped into a depositor system that lays a continuous sheet of caramel over the cooled nougat ribbons. This depositor uses pressurized nozzles that spread the caramel evenly across the top surface of the nougat. The caramel is still warm and pliable at this point, allowing it to form a tight bond with the underlying layer. As the conveyor continues to move, the nougat and caramel combination enters another cooling tunnel, where the caramel layer is firmed to a stable consistency. Here again, the temperature gradient is critical. The cooling must be fast enough to stop flow, but slow enough to avoid separating from the nougat base. After the caramel is stabilized, whole roasted peanuts are applied. Snickers uses high-grade peanuts that are dry roasted on-site or sourced from dedicated peanut processors. These peanuts are first cleaned, sorted, and passed through color and size grading machines. Roasting is carried out in rotary drum roasters, where temperatures are maintained around 160 degrees Celsius. After roasting, peanuts are cooled rapidly using ambient or force-chilled air to stop the cooking process and retain crunch. The cooled peanuts are then sprinkled over the still sticky caramel layer using a controlled vibratory feeder. These feeders dispense peanuts in an even distribution, and excess nuts are collected and recirculated to avoid waste. Once applied, the peanut caramel nougat stack moves through a compression station where soft rollers press the peanuts gently into the caramel to ensure adhesion. This step is essential to prevent peanuts from falling off during enrobing and packaging. The multi-layer slab is then cut again, first lengthwise into individual bar width strips, then crosswise into single units. High-speed ultrasonic knives are often used in this phase to make clean cuts through the sticky peanut caramel mass without dragging or deforming the shape of the bar. These knives vibrate at ultrasonic frequencies, reducing friction and keeping each cut smooth and precise. As with earlier cutting stages, sensors track bar dimensions, and any piece that falls outside specified tolerances is rejected automatically. Now, the cut bars are conveyed into the enrobing chamber, where they are coated with milk chocolate. The chocolate used in Snickers is a proprietary milk chocolate blend containing cocoa solids, cocoa butter, sugar, milk powder, and emulsifiers. This chocolate is kept in tempering tanks where it is heated and cooled in a controlled cycle to form stable cocoa butter crystals. Proper tempering is crucial for ensuring that the chocolate coating is glossy, has the right snap, and doesn't develop fat bloom over time. Inside the enrober, each bar passes over a fine mesh conveyor that dips the underside of the bar in chocolate. A curtain of tempered chocolate then flows over the top of each bar, fully enrobing it. Excess chocolate is removed by controlled air jets or vibrating mechanisms, which ensure a consistent coating thickness without pooling or streaking. As the chocolate sets, decorative ribbons or textures may be applied to the top surface using nozzles or air patterns. After enrobing, the bars enter the final cooling tunnel. This tunnel is typically 20 to 30 meters long and divided into multiple zones, with temperatures gradually decreasing from around 15 degrees Celsius to 5 degrees Celsius. The goal here is to allow the chocolate to crystallize into a firm, uniform shell without cracks or surface defects. Conveyor speed and cooling tunnel temperature are constantly adjusted to account for changes in factory humidity or chocolate flow rate. Once the bars exit the cooling tunnel, they move to the packaging area. Here, vision systems inspect the bars for defects, such as incomplete coating, misshapen forms, or incorrect size, and reject any units that don't meet quality standards. Accepted bars move into a high-speed flow wrapping machine. This machine dispenses printed plastic film from large rolls, forms it into a sleeve around each bar, seals the ends and back, and prints lot numbers, expiration dates, and traceability codes onto the packaging. Bars are grouped and packed into cartons automatically, then palletized using robotic arms or automatic stackers. Each pallet is labeled with its production date, factory ID, and batch number, and stored in a temperature-controlled warehouse. Finished Snickers bars are shipped daily to retailers, wholesalers, and export hubs with real-time tracking through the company's logistics and ERP systems. This ensures traceability from raw ingredient to retail shelf and allows for rapid recall or investigation if any quality issue arises in the field. Snickers production is supported by continuous quality assurance throughout every phase. From incoming raw ingredients to the final product, quality technicians perform random sampling and laboratory testing for moisture content, peanut roast quality, chocolate temper index, caramel viscosity, and microbial counts. Every component, nougat, caramel, chocolate, peanuts, is monitored to within narrow tolerances. If even a single component batch shows deviation, it can be traced, flagged, and excluded from the production cycle. In addition to quality, food safety and hygiene are rigorously maintained. All machinery is subject to clean-in-place protocols, and workers adhere to strict sanitation and allergen handling rules. Due to the presence of peanuts, dedicated production zones and air handling systems are used to prevent cross-contamination with other product lines in multi-product factories. The Snickers production process is also increasingly supported by digital technology. Smart sensors, machine learning models, and real-time analytics are used to monitor equipment performance, detect subtle variances, and suggest preventative maintenance. Digital twins of the production line can simulate different production scenarios, like ingredient substitutions or temperature fluctuations, to predict impacts before they occur in the real world. This data-driven approach allows Mars, Inc., the manufacturer of Snickers, to continuously refine and optimize its production across multiple global sites. Twix is a beloved chocolate bar recognized globally for its iconic combination of crisp biscuit, chewy caramel, and smooth milk chocolate. Its appeal lies in the precise layering and the uniformity with which each bar delivers the same balance of texture and flavor. Behind its simple appearance is a highly engineered manufacturing process that seamlessly integrates baking, confectionery science, and automated packaging on a vast industrial scale. Producing millions of Twix bars daily in factories around the world requires meticulous coordination across every step of production, from dough mixing to chocolate enrobing, all operating under strict food safety protocols and quality control systems. The following in-depth look walks through the entire process, detailing how Twix is made in a modern factory environment, step by step, with over 1,600 words devoted to the subject. The process begins with the foundation of the Twix bar, the biscuit base. This shortbread-like component is central to the signature texture of Twix, light, crunchy, and buttery without being too sweet. The ingredients for the biscuit base include wheat flour, vegetable oil or shortening, sugar, salt, and leavening agents. These raw materials are delivered to the facility in bulk, typically stored in stainless steel silos or sealed containers to protect against moisture and contamination. The dry ingredients are conveyed into high-capacity horizontal mixers, where they are combined with fats and a small amount of water. These mixers are programmed to replicate the specific time, temperature, and mixing intensity needed to create the ideal dough consistency. Overmixing is carefully avoided to prevent gluten development, which would make the biscuit tough rather than tender and crisp. The dough is monitored for temperature, moisture content, and texture using inline sensors, ensuring consistency across every batch. Once mixed, the dough is transferred to a sheeting machine. This equipment rolls the dough into a uniform sheet of precise thickness, typically between 5 to 7 millimeters, depending on the specific product variant. The sheet passes through multiple sets of rollers to ensure evenness, then moves toward a rotary cutter that stamps out the biscuit fingers. Each finger is carefully spaced on a baking band to prevent sticking or deformation during baking. Excess dough, or webbing, is collected automatically, recycled, and fed back into the mixer for reuse, minimizing waste. The cut biscuits are conveyed into a tunnel oven, often more than 30 meters long, and divided into multiple temperature zones. The ovens are typically gas-fired and utilize forced convection to ensure even heat distribution. Baking profiles are carefully managed. The temperature starts lower to allow for expansion and rises toward the middle and end of the tunnel to set structure and achieve the golden brown exterior. The baking process typically lasts around 8 to 12 minutes. The final product emerges dry, crisp, and structurally sound to support the next layers of caramel and chocolate. After baking, the biscuits are cooled on a long spiral or tiered cooling conveyor. It is essential that they reach ambient temperature before caramel application, as residual heat could soften the caramel or cause bonding inconsistencies. Airflow systems within the cooling unit are calibrated to prevent moisture buildup, which could compromise the crispness of the biscuit layer. Next is the caramel layer, one of the most technically challenging aspects of the Twix manufacturing process. The caramel must be viscous enough to form a thick, even layer on the biscuit, yet firm enough to retain its shape during cutting, enrobing, and packaging. It must also stretch slightly when bitten into, without melting or breaking apart. The caramel is prepared in large, jacketed cooking kettles or continuous caramel cookers. The ingredients: glucose syrup, sugar, milk solids, fats, and sometimes salt and flavorings are heated to a controlled temperature around 118 to 120 degrees Celsius. Cooking caramel to the correct temperature is critical. Any deviation can result in too hard or too runny caramel. The factory's automated control systems monitor bricks levels, temperature curves, and viscosity in real time. Adjustments are made instantly if readings deviate from the set parameters. Once cooked, the caramel is pumped into a depositor system. This system deposits a continuous ribbon of hot caramel directly onto the cooled biscuit fingers, which are now moving along a precision conveyor belt. Depositors can be adjusted to control caramel height and width, ensuring even coverage. The caramel must adhere firmly to the biscuit and cool rapidly to a semi-firm consistency to hold its shape through the subsequent chocolate enrobing process. The bars now enter a cooling tunnel for caramel setup. This tunnel is maintained at a lower ambient temperature and spans several meters to allow gradual cooling without thermal shock. As the caramel cools, it solidifies just enough to support chocolate coating without running or shifting. This balance is critical for appearance, structural integrity, and mouthfeel. Once the biscuit and caramel layers are firmly bonded, the bars proceed to the chocolate enrobing phase. This is where each Twix bar is fully coated in a layer of milk chocolate. The chocolate used is a proprietary blend formulated specifically for Mars, Inc., and it includes cocoa butter, milk powder, cocoa solids, sugar, and emulsifiers, such as soy lecithin, to ensure proper flow. The chocolate is first tempered, a process that involves heating, cooling, and reheating to encourage the formation of stable cocoa butter crystals. Proper tempering gives the final chocolate coating its shine, snap, and resistance to fat bloom. In large-scale operations, tempering is achieved using continuous tempering machines that monitor crystal formation, viscosity, and flow rate. The tempered chocolate is pumped into an enrober, which is essentially a tunnel where a curtain of chocolate flows from above and a shallow pool coats the bottom. The bars pass through this curtain and are submerged briefly in the bottom coating layer, ensuring all sides are covered. Air knives or vibrating plates remove excess chocolate, and decorative features, such as surface ripples, may be added by adjustable nozzle heads or vibration patterns. The chocolate-coated bars are immediately conveyed into another cooling tunnel, this one much longer and colder, designed to gradually bring the chocolate to a solid state without creating bloom or surface imperfections. The cooling tunnel maintains a strict temperature gradient, starting around 18 degrees Celsius and lowering to 10 degrees Celsius by the end, over a 5 to 10 minute period. As the bars exit the cooling tunnel, they are fully formed Twix bars, but they're not yet individually packaged. They move directly into the high-speed wrapping area. Each bar is aligned and spaced using puck systems or lane guides to ensure it enters the flow wrapping machine correctly. Here, rolls of branded film are fed into the wrapper, folded tightly around the bar, and sealed on all sides using heat and pressure. The film is pre-printed with logos, batch codes, nutritional data, and sometimes promotional graphics. Each wrapped bar is weighed and passed through metal detectors or X-ray scanners to ensure it meets food safety standards. Any bar outside of weight tolerance or showing contamination is automatically diverted. Accepted bars are grouped into multi-packs or display boxes using robotic pickers or diverters, then loaded into shipping cartons. The cartons are coded with tracking data and palletized using automatic palletizers. Each pallet is scanned into inventory and staged for shipping. Throughout the factory, quality control technicians pull samples at regular intervals to test for key performance attributes: biscuit density, caramel thickness, chocolate adhesion, weight, sensory characteristics, and packaging integrity. The factory also operates under a HACCP framework, meaning each step of the process is mapped for potential hazards and monitored with critical control points. Twix manufacturing is highly dependent on repeatability, and thus, much of the factory's infrastructure is built around statistical process control and automation. PLCs communicate with sensors on every machine, feeding data to a centralized control room. This enables supervisors to watch live readouts of oven temperatures, caramel cooker output, chocolate temper readings, fill weights, and wrapper speed, all updated every second. Alarms and automatic corrections are built into the system, allowing for real-time adjustments without stopping production. Beyond process precision, Twix production lines are designed for flexibility. Factories can run product variations including Twix miniatures, Twix ice cream bars, Twix cookies and cream, or seasonal additions like white chocolate or dark chocolate. Changeovers between product formats involve switching molds, adjusting depositor nozzles, changing film rolls, and flushing chocolate lines, all of which are guided by detailed standard operating procedures to avoid cross-contamination and ensure food safety. Once finished, Twix bars are shipped to distribution centers or directly to retailers. During shipping, temperature control remains important, particularly in warm climates where chocolate is susceptible to melting. Pallets may be moved using temperature-controlled trucks or packed with insulation to protect product integrity. Inventory is rotated on a first-in, first-out basis to ensure freshness and shelf life management. At the retail end, Twix must retain not only its visual appeal, but its textural signature. The snap of the biscuit, the chew of the caramel, and the smoothness of the chocolate are all the result of hundreds of synchronized steps and checks across a production system built for consistency at scale. From ingredient sourcing to the final shipping pallet, every detail is fine-tuned to preserve the brand's identity and ensure that each bite of Twix tastes exactly as expected: crisp, creamy, and perfectly layered. It all begins with the peanuts. While it might seem obvious that a peanut butter cup would start with peanuts, what's not widely known is just how much control and specificity Hershey applies to this ingredient before it ever reaches the cup itself. Reese's production lines require massive quantities of peanuts, hundreds of tons per week across facilities, and not just any peanut will do. The factory demands high oleic runner peanuts, most commonly sourced from farms in Georgia, Alabama, and Texas. These peanuts are preferred for their uniform kernel size, mild flavor, and high oil content, which delivers a creamier peanut butter base. Once harvested, peanuts are sent to dedicated shelling and blanching facilities, where they are cleaned, sorted, and skinned. The outer red skins are removed through dry abrasion, and the kernels are visually and electronically inspected to eliminate any with defects, mold, or foreign materials. Only the highest grade peanuts, typically designated as US Fancy or US Extra Large, are accepted for Reese's production. These peanuts are then loaded into food-grade hoppers and shipped in sealed bulk containers to the peanut butter manufacturing lines at Hershey's centralized processing plants. Upon arrival at the factory, the peanuts are stored in stainless steel silos within a climate-controlled environment to prevent spoilage. Prior to use, the peanuts are metered into roasting drums. Roasting is a critical step not just for flavor, but for aroma development and moisture reduction. High-capacity rotary roasters or continuous conveyor-style roasters are used, depending on the factory's line design. Peanuts are typically roasted at temperatures between 320 degrees Fahrenheit and 360 degrees Fahrenheit for 30 to 45 minutes. The exact temperature curve is adjusted based on peanut moisture and oil content, which is sampled batch by batch in the factory's lab using gas chromatography and moisture analyzers. The roasters are equipped with air impingement systems and inline sensors to monitor internal temperature, color, and roast development in real time. At various intervals, small test samples are pulled using auto draws for taste panel review. Roast level has to be absolutely consistent, as this is the foundation for the signature Reese's peanut butter flavor. Over-roasted peanuts will produce a burnt or overly bitter taste, while under-roasting leaves the flavor bland and oily. Once roasted, peanuts are cooled using high-powered air chillers to prevent overcooking and to stabilize the oils. They are then conveyed into degermers and mechanical splitters, where they are cracked open and the hearts, the hard inner core of the peanut, are removed. These hearts, while technically edible, can impart a bitter or chalky aftertaste, so they are separated out and typically used in livestock feed or secondary food processing streams. Now comes the grinding phase. The roasted and cooled peanuts are fed into large, high-shear grinders, industrial versions of what's used in commercial peanut butter production. These grinders operate at extremely high RPMs and are often configured in a two-stage system: a coarse grind followed by a fine grind. In the coarse phase, the peanuts are broken down into a grainy paste, preserving small particulates that contribute to the slightly gritty texture of Reese's peanut butter. This paste is then piped into a second mill, where it's refined to a smooth, uniform consistency. The peanut paste is blended in stainless steel mixing tanks equipped with variable speed paddles and heated jackets. At this stage, a proprietary mix of additional ingredients is incorporated. These include salt, sugar, a small amount of fully hydrogenated vegetable oil, and a dry milk derivative. The sugar used is finely milled and sieved to a consistent particle size, ensuring it disperses evenly throughout the mix without recrystallizing. Emulsifiers such as mono and diglycerides are added in microdoses, enabling the fat and protein phases to remain homogeneous over time. What makes Reese's filling unique, and one of the factory's guarded secrets, is its texture. It isn't traditional creamy peanut butter. It's dry and crumbly, almost fudge-like, but melts smoothly on the tongue. This is achieved by very specific moisture and fat content targets. The factory carefully controls the fat ratio in the peanut blend using inline nuclear magnetic resonance sensors, which measure fat levels without destroying samples. The ideal balance results in a pliable, moldable filling that holds its shape during chocolate enrobing but softens under bite pressure. Once blended, the peanut butter filling is pumped into chilled hoppers and held at precise temperature, typically between 60 degrees Fahrenheit and 70 degrees Fahrenheit, so it can be extruded or deposited with exact weight and shape control. Temperature consistency is crucial here. Too warm, and the filling becomes too soft and spreads when deposited. Too cold, and it hardens and resists clean shaping, risking damage to the chocolate cup. The final stage in this first segment is the formation of the peanut butter centers. On a separate production line, the cooled peanut filling is portioned using servo-driven pistons or extrusion rollers, depending on the cup format being produced. These machines deposit small, perfectly measured mounds of filling onto a chilled conveyor. In larger cups, the filling is puck-shaped. In minis, it's closer to a small dome. Each peanut butter deposit is then transferred into a temporary holding tunnel, essentially a refrigeration corridor, where the shaped fillings are stabilized prior to the chocolate enrobing phase. Here, humidity and temperature are carefully balanced to avoid condensation or fat bloom when chocolate is later applied. At this point, the peanut butter centers are firm, uniform in size and shape, and fully ready for the next critical phase of the process, chocolate molding. With the peanut butter centers now precisely formed, cooled, and stabilized, The next critical phase in the industrial production of Reese's peanut butter cups begins: chocolate shell creation and cup assembly. This portion of the process is all about precision, timing, and the seamless integration of multiple complex systems to produce a product that's visually perfect and texturally balanced. It's here that the familiar cup shape begins to take form, and where Hershey's decades of manufacturing expertise are on full display. The chocolate used in Reese's products is developed in-house and differs slightly from that used in a Hershey's milk chocolate bar. While it still contains cocoa solids, cocoa butter, milk solids, sugar, and lecithin, it has been tailored specifically to pair with the salty sweet peanut butter filling. The chocolate is slightly softer in melt, less bitter than dark chocolate, and has a fat and sugar profile that ensures it doesn't overpower the filling. It's formulated to be both moldable and stable under typical shelf conditions, even in warmer climates. The chocolate arrives at the cup production line in a liquid state, held in large tempering tanks kept at a precise temperature, usually around 30 to 32 degrees Celsius for milk chocolate. Tempering is an essential part of chocolate manufacturing and involves heating the chocolate to fully melt its cocoa butter crystals, cooling it to initiate the formation of stable type 5 crystals, then gently reheating it to bring it to working temperature. This process ensures that once the chocolate is set, it has a glossy finish, resists bloom, and has a clean snap when broken. The first step in forming the Reese's cup is lining the signature brown paper cup mold with chocolate. The production line is fed with pre-formed paper cups stored in large reels or stacked columns that are automatically dispensed onto a high-speed conveyor. These paper cups are food-grade, waxed, or coated with a thin moisture barrier and shaped precisely to hold their structure during and after chocolate deposition. Once the paper cups are set in place on the moving line, a chocolate depositor head releases a measured dose of tempered chocolate into each one. This is known as the bottoming phase. The amount of chocolate is critical, not only for structure, but also for controlling the ratio of chocolate to filling. After deposition, the cups pass over a vibration table. This stage is crucial for evenly spreading the chocolate along the bottom and slightly up the sides of the paper cup. The vibration table uses rapid, controlled pulses to remove air bubbles and to ensure a uniform shell that won't crack or collapse during filling. Immediately following the bottoming step, the peanut butter centers are dropped into the liquid chocolate. These centers have been transferred from the refrigerated holding tunnel to the enrobing line and are picked and placed with robotic arms or pneumatic suction systems that gently lower each piece into its corresponding chocolate-lined cup. The timing of this placement is perfectly synchronized so that the peanut butter slightly sinks into the chocolate but doesn't hit the bottom, allowing a chocolate base to remain intact beneath the filling. As the peanut butter sits in the base, a second dose of chocolate is deposited on top. This is referred to as the capping phase. The capping head delivers another precise amount of tempered chocolate to completely enrobe the peanut butter core. This top layer seals the filling, ensuring the product is fully enclosed and protected from oxygen, moisture, and contamination. The final thickness of the cap is carefully calibrated, so the chocolate shell is strong enough to hold shape, but still soft enough to bite through easily without excessive crumbling. The assembled cups, now complete with base, filling, and cap, are conveyed into a long, multi-zone cooling tunnel. These tunnels are often 20 to 30 meters in length and feature graduated temperature zones, starting at around 16 degrees Celsius and dropping to 8 to 10 degrees Celsius toward the end. The slow, controlled cooling is essential to prevent condensation or stress fractures in the chocolate. Too rapid a chill can cause bloom or cracking, while uneven cooling can result in misshapen edges or textural inconsistency. Inside the cooling tunnel, conditioned air circulates in laminar flow patterns, ensuring that every cup is exposed to identical cooling conditions. The duration of the tunnel cycle is calibrated to match line speed and product size. Larger Reese's big cups may require longer chill times compared to the classic or miniature versions. At the tunnel exit, the cups are inspected by automated vision systems that detect anomalies like off-center fillings, insufficient chocolate coverage, or edge deformation. Any defective cups are automatically diverted from the line for reprocessing. The cups that pass inspection are ready for packaging. But before that happens, there's one last critical test: weight and sealing verification. Inline check weighers use load cells to weigh each cup or group of cups to ensure they fall within designated tolerances. Simultaneously, barcode scanners and optical sensors check that each product is aligned and properly seated in its paper cup. The final stage before wrapping is an air dusting system that removes chocolate crumbs, static particles, or paper fragments from the surface to ensure a clean, polished presentation in the final package. Packaging of Reese's cups is a high-speed operation. Cups are grouped automatically into configurations appropriate for each product format: singles, twin packs, snack size multi-packs, or seasonal variations. Each group is loaded into a continuous film wrapping machine, which pulls branded plastic film from a roll, wraps it around the cups, seals it with a heated crimper, and cuts it into individual packages. The film is pre-printed with product information, UPC codes, and freshness dates that were applied earlier by industrial flexographic printers. Once wrapped, the products pass through another metal detector or X-ray system to detect any foreign contamination that may have occurred during packaging, a standard in modern food manufacturing. Any anomaly results in immediate ejection and shutdown of the machine until the issue is resolved. The acceptable product continues to cartoning lines, where it is packed into retail-ready boxes, display trays, or bulk shipping cases depending on the destination. Finished product cartons are coded, palletized by robotic stackers, and shrink-wrapped for transport. Each pallet is labeled with a unique tracking number that links it to its production batch, shift number, ingredient lot codes, and quality control logs. This traceability allows for quick response in case of any issues in the supply chain. Every Reese's Peanut Butter Cup batch is subject to a comprehensive quality assurance protocol from start to finish. While visual inspection, weight checking, and foreign material detection handle surface-level defects, deeper analytical testing is performed regularly throughout production. Factory labs adjacent to the production floor run hourly tests on product samples pulled from the line. These tests measure water activity, pH levels in the peanut filling, chocolate temper index, fat content, and emulsifier concentration. Advanced equipment like near-infrared spectrometers and gas chromatographs are used to validate these metrics with precision. In addition to instrument-based testing, trained sensory panels perform blind evaluations of finished product samples. These panels, often composed of factory employees specially trained in flavor and texture recognition, assess everything from peanut aroma intensity to shell firmness, sugar balance, and mouthfeel contrast between chocolate and filling. Feedback from these panels is compared to golden standard benchmarks. Reference Reese's cups produced under ideal conditions that are stored in temperature and humidity-controlled archives. These control cups are regularly reviewed to ensure no drift in product quality over time. Allergen control is one of the most sophisticated systems running silently beneath the surface of Reese's production. Since peanuts and dairy are both major allergens, Hershey facilities that manufacture Reese's operate under strict protocols to prevent cross-contamination. Separate ingredient receiving docks, isolated storage silos, color-coded tool systems, and dedicated air handling zones are used to segregate peanut-related materials from other production lines within the same facility. Sanitation crews follow clean-in-place procedures using food-safe alkaline and acid-based cleaners to remove all traces of allergens between product changeovers. Swab testing for peanut protein residue is conducted on all contact surfaces before production resumes. Hershey also enforces supplier controls. All incoming peanut shipments are tested for aflatoxins, a class of toxic compounds produced by certain molds that can occur in improperly stored peanuts. Only peanuts that pass stringent safety thresholds are accepted, and each delivery is logged and tracked using batch codes that link to the final product's traceability system. This digital record keeping allows Hershey to track every ingredient back to its source farm and forward through every unit sold. But Reese's isn't just a singular product anymore. Over the years, the brand has expanded into dozens of variations: white chocolate cups, dark chocolate, big cups, miniatures, stuffed versions with pretzels, potato chips, Reese's Pieces, or caramel. Each variant requires its own unique processing conditions and introduces new complexity to the factory system. Let's take the white chocolate Reese's as an example. This variation uses a cocoa butter-based confectionery coating rather than traditional milk chocolate. It must be handled in separate melters and tempering systems due to its sensitivity to high heat and faster tendency to bloom. White chocolate also requires precise control of ambient light and humidity during production and packaging, as it is more susceptible to visual imperfections. On the line, switching from standard milk chocolate to white chocolate triggers a full line cleaning and recalibration of depositor and cooler settings. Flavor variants with inclusions, like Reese's with Reese's Pieces inside, add another layer of complexity. In these formats, the peanut butter filling is first blended with the inclusion, pieces, chips, or even candy bits, using slow-speed paddle mixers to avoid crushing or melting the added components. These inclusions alter the viscosity and extrusion behavior of the filling, requiring depositor nozzles to be widened and dosing pumps to be recalibrated for accurate weight control. Additionally, because candy-coated pieces can crack or leak color when exposed to oil migration from the peanut butter, the storage conditions of these fillings must be tightly managed to preserve structural integrity during molding. Even packaging formats are adapted. Big cups, which contain more filling and sometimes additional elements, require thicker paper cups and slightly wider flow wrapping machines to handle the larger size. Seasonal versions, like pumpkin-shaped Reese's for Halloween or tree-shaped cups for Christmas, require completely new mold tooling, reshaped paper cups, and different wrapping film dimensions. These seasonal SKUs are often produced in limited time production runs scheduled between mainline batches, with precise coordination between departments to minimize downtime and clean out inefficiencies. To manage this growing complexity, Hershey's manufacturing ecosystem is deeply integrated with real-time data and automation. Programmable logic controllers govern every stage of production, from peanut grinding to chocolate capping. These controllers constantly adjust conveyor speeds, depositor volumes, oven temperatures, and cooling rates to match product specifications in real time. Sensors along the line feed back information on humidity, belt tension, machine vibration, and material flow. If any parameter drifts beyond the preset tolerance window, an alert is triggered immediately and logged by the manufacturing execution system. The MES serves as the brain of the operation. It logs every batch, shift, operator, ingredient lot, and test result. It manages production schedules based on demand forecasting from Hershey's enterprise planning systems, and it ensures the right packaging, ingredients, and machines are prepared for the next product variation before the current one is even complete. The MES also interfaces with digital traceability systems, allowing Hershey to execute complete recalls if necessary, though this is extremely rare due to the redundant safety nets in place. To support sustainability goals, the factory also measures key environmental metrics, Energy usage from roasting, tempering, and cooling operations is tracked and optimized. Waste heat from roasters is sometimes redirected to preheat water for sanitation systems. Chocolate scrap from edge trimmings and overflows is collected and reworked in designated reclaim tanks. Even the cardboard used for cartons and paper used for wrapping is sourced from certified sustainable forestry programs. Water used in cooling tunnels is recirculated through industrial-grade filtration systems and UV sterilization loops, allowing for multiple reuse cycles before any disposal. Factory roofs are often equipped with solar panels, contributing to the site's renewable energy footprint. These sustainability measures not only support Hershey's corporate goals, they also help reduce operating costs and ensure compliance with international environmental standards, especially for exports to markets with strict eco-regulations. Finally, at the distribution level, finished pallets of Reese's are scanned, shrink-wrapped, and entered into a dynamic warehousing system. Pallet storage is optimized by weight, sell-by date, and destination zone. Reese's products are shipped in refrigerated trucks when needed, although standard varieties are stable at room temperature due to their low water activity and solid fat matrix. Shipments are tracked via GPS and load sensors to ensure they remain within safe handling conditions throughout transit. So when you open a Reese's peanut butter cup and experience the snap of chocolate, the softness of the peanut filling, and the perfectly even texture from edge to edge, what you're actually tasting is the output of a meticulously engineered, continuously monitored, and relentlessly optimized factory system. Behind every wrapper is a chain of roasting drums, tempering tanks, vibration tables, chilled tunnels, microlab samplers, PLCs, conveyors, AI sensors, and hundreds of trained hands working in quiet unison to make every bite familiar, reliable, and timeless. As Reese's peanut butter cups leave the controlled environment of production and are loaded onto outbound trucks, the story doesn't end with the last machine seal or pallet scan. In fact, one of the most underappreciated aspects of the manufacturing system lies in how Reese's maintains product integrity far beyond the factory walls. The journey from factory to store shelf, and ultimately to the consumer's hand, is an extension of the manufacturing process itself. For a product like Reese's, where texture, flavor, and structure are so carefully engineered, maintaining those qualities through shipping, storage, and retail presentation is non-negotiable. Temperature control plays a key role in this extended quality assurance chain. While Reese's peanut butter cups are classified as shelf-stable and do not require refrigeration, they are extremely sensitive to heat and humidity. Elevated temperatures can cause the chocolate to melt or bloom, a condition where cocoa butter rises to the surface and creates a whitish grey coating. Though harmless, bloom gives the appearance of staleness or spoilage and is unacceptable in any retail-facing product. To prevent this, shipping containers and trucks are monitored using digital temperature loggers and GPS trackers. These devices not only ensure compliance with storage requirements, but also provide real-time alerts if conditions fall outside predefined thresholds. Warehousing and retail logistics are optimized with similar care. Distribution centers receiving Reese's shipments are instructed to rotate inventory on a strict first-in, first-out system to preserve freshness. Shelving time is tracked down to the day, with expiration dates digitally logged and printed clearly on all packaging. Retailers are often supplied with merchandising guidelines from Hershey's sales and operations teams, advising on optimal product placement to avoid heat sources and maintain visibility in high-traffic zones. This ensures not just product survival, but also consumer engagement. Meanwhile, Hershey's central data systems stay connected to the broader supply chain. Sales velocities from thousands of retail points are monitored using automated inventory systems that integrate with distribution algorithms. If Reese's products are selling faster than expected in one region, perhaps due to a seasonal promotion or viral social media trend, production forecasts and shipment routes are adjusted in near real time to prevent outages. Conversely, if stock is underperforming, the system can slow production or reroute product to a region with higher demand. But what truly sets Reese's apart in this final segment of its manufacturing cycle is its flexibility for innovation and customization, especially on a global scale. Reese's peanut butter cups aren't manufactured identically across every country. Although the core elements remain the same, formulations may be slightly adjusted to meet regional preferences, regulatory standards, or ingredient availability. For example, Reese's produced for the European market may contain non-GMO ingredients or use different emulsifiers to comply with EU food safety regulations. Sugar content, fat ratios, and even packaging inks are tailored to local markets, and each international facility must pass regional audits to ensure compliance with both Hershey standards and those of the target nation. Seasonal and limited edition Reese's lines introduce another layer of production complexity that extends into post-factory strategy. Every year, variations such as pumpkin-shaped Reese's in October, tree-shaped ones in December, and heart-shaped versions for Valentine's Day hit the shelves. These products require not only physical retooling, custom molds, unique wrappers, modified flow wrappers, but also adjusted production timelines to accommodate pre-holiday distribution. Most holiday variants are produced months in advance to ensure they hit retail shelves in time for the season, but remain fresh through the actual holiday window. To ensure holiday versions meet the same performance standards as core SKUs, Hershey uses accelerated shelf life testing. In these tests, products are stored at elevated temperatures and humidity for a condensed time frame to simulate long-term storage. The samples are then analyzed for fat migration, filling breakdown, wrapper integrity, and flavor degradation. Only those variants that meet Reese's strict internal benchmarks for shelf life, texture stability, and visual appearance are approved for full-scale seasonal release. The journey to create a Ferrero Rocher begins long before any chocolate is tempered or gold foil is wrapped. At its heart lies a hazelnut, and not just any hazelnut. Ferrero sources its hazelnuts primarily from its own agricultural subsidiaries across Italy, Turkey, Chile, and the United States, maintaining vertically integrated supply chains. The factory only uses specific cultivars with a consistently round shape, low moisture content, and a rich, buttery flavor profile. These hazelnuts are known for their roasting performance and uniformity, which are critical in a process that scales to millions of pieces per day. Upon arrival at the production facility, the hazelnuts are unloaded from sealed food-safe bulk containers and moved directly into raw material intake silos. These silos are temperature and humidity controlled to prevent moisture absorption or rancidity. Before they're accepted into the main line, samples from every incoming batch are tested in the factory's on-site lab. Here, chemical composition, size, oil content, and shell integrity are measured. Random nuts are dissected and inspected for mold, aflatoxins, or insect damage. Only batches that meet Ferrero's strict tolerances pass through to the next phase. After intake, hazelnuts go through an intensive cleaning and sorting phase. Pneumatic air classifiers remove light foreign material like leaves or twigs, while vibratory sieves and optical sorters remove undersized, broken, or discolored nuts. The next step is roasting, a critical transformation stage that dictates the final flavor of the entire chocolate. The factory uses continuous belt roasters or fluidized bed systems that allow precise control over temperature and airflow. The hazelnuts are roasted at temperatures between 140 degrees Celsius and 160 degrees Celsius for 15 to 25 minutes, depending on moisture content and target flavor development. The roasters are outfitted with inline sensors that continuously monitor temperature, kernel color, and weight loss. Each nut is tracked by its lot number, and roast profiles are tailored to each batch to ensure consistency. Once roasted, the hazelnuts are cooled rapidly using forced air cooling systems to prevent over-roasting and to stabilize the oils. The now crispy skins are loosened during roasting and are removed in large-scale abrasive peelers, machines that spin the nuts against fine-textured rubber belts, stripping away the skins without damaging the core. At this point, a percentage of the roasted, peeled hazelnuts are set aside for whole use. These will eventually form the central core of each Ferrero Rocher, but the majority are transported into grinding and blending stations for the creation of Ferrero's ultra-smooth Gianduja-style filling, which sits just beneath the shell. The nuts designated for filling are passed through industrial conching grinders. These high-speed systems generate heat through friction, reducing the hazelnuts into a fine paste known as hazelnut butter. The paste is blended with powdered sugar, milk solids, cocoa powder, and a small amount of vegetable oil to create the silky, nutty filling that defines the brand. The consistency of this hazelnut cream must be exact. Viscosity is measured continuously using inline viscometers, while fat content and particle size distribution are tracked in the lab. The filling needs to remain soft and pipeable at controlled temperatures, but must also resist oil separation over its shelf life. To achieve this, Ferrero employs emulsifiers and stabilizers, but in meticulously optimized concentrations, ensuring that the flavor of the nuts remains dominant while the texture holds up over time. The finished filling is held in jacketed stainless steel tanks with gentle agitation to keep it homogeneous. These tanks are connected to piping systems that lead to the next station, center formation. This is one of the most mechanically intricate parts of the Ferrero Rocher manufacturing process. A specialized depositor machine injects a portion of the hazelnut cream into preformed chocolate wafers, while simultaneously placing a whole hazelnut directly into the center. These wafers are precision-molded hemispheres, delicate yet structurally rigid enough to hold filling without cracking. The depositor head works at high speed, aligning cream, hazelnut, and wafer half shell in one synchronized motion. Once filled, two hemispheres are pressed together with precise pressure and rotation to create a sealed, spherical core. The seam is smoothed by a heated rolling chamber, which blends the edges of the wafer halves together, using just enough thermal energy to fuse without over-softening. At this stage, the product is still structurally vulnerable, so it is immediately transferred to a cooling zone. In this controlled tunnel, ambient temperature is gradually reduced to stabilize the hazelnut cream and harden the wafer shell. Airflow is carefully directed to prevent condensation or uneven cooling. The spheres are rotated during cooling to maintain shape and uniformity. With the fragile hazelnut-filled spheres now stabilized after cooling, the next phase of Ferrero Rocher's industrial creation process moves into what may be its most visually iconic stage, the chocolate coating and enrobing line. Here, the spheres are transformed from delicate, pale wafer-based cores into gleaming orbs of textured chocolate and crushed hazelnuts. This phase demands tight control over temperature, viscosity, and timing, requiring highly specialized machinery to create the exact visual and sensory texture Ferrero is known for around the world. The first step in this phase is called pre-coating. Before applying the outermost layer of chocolate and hazelnut granules, the wafer spheres must be sealed in a protective chocolate coat that both strengthens the structure and acts as a moisture barrier. The wafer shell, while crisp and delicate, is porous and hydrophilic, meaning that without a sealed layer of fat-based coating, it could absorb moisture from the surrounding air or filling and go soft. To prevent this, the cooled spheres are conveyed into a rotary enrobing drum. This drum is a rotating stainless steel barrel with angled internal fins. It slowly tumbles the spheres while fine jets of tempered chocolate are sprayed from nozzles arranged in concentric rings. This chocolate, made from a proprietary blend of milk solids, cocoa butter, cocoa liquor, and sugar, is pre-tempered to ensure crystallization structure, gloss, and a smooth mouthfeel. The chocolate is pumped from a heated reservoir kept at a strict 31 to 32 degrees Celsius, the ideal working range for enrobing milk chocolate. As the spheres tumble through the drum, the thin spray of chocolate coats them evenly. The rotation ensures every surface is touched without allowing pooling or excessive buildup. Each sphere passes through this drum for approximately 15 to 20 seconds, enough time for full coverage, but short enough to avoid heat penetration that might soften the core. Once coated, the spheres move immediately into a cooling tunnel, a long, gradually chilling corridor where the chocolate layer is allowed to set. This tunnel maintains an ambient environment of 10 to 12 degrees Celsius with less than 50% humidity, ensuring the chocolate hardens smoothly and with the correct crystalline form. Next comes one of Ferrero Rocher's most defining sensory features, the rough, nutty exterior. To create this, the cooled, pre-coated spheres are passed through a second enrobing station where they receive a final coating of chocolate mixed with crushed roasted hazelnut fragments. This mixture is stored in a jacketed mixing kettle that gently stirs it to keep the nut pieces evenly suspended in the chocolate. The chocolate itself is slightly more viscous than the pre-coat formulation, engineered to hold the heavier particles in suspension while still flowing smoothly over the spherical surfaces. At this enrobing station, the spheres pass under curtain-style chocolate waterfalls, controlled flows of chocolate hazelnut mixture that cascade down over them as they move along a vibratory conveyor belt. As each sphere receives this layer, it is gently rocked back and forth to distribute the coating evenly and prevent accumulation on one side. Immediately afterward, the coated spheres pass beneath precision air knives, thin, high-velocity streams of air that remove excess chocolate while preserving the textured, lumpy appearance of the nut coating. The airflow is adjusted based on real-time feedback from load cells, measuring the weight of sample pieces exiting the line. This final chocolate nut layer adds both crunch and the brand's signature visual finish. But just like the first chocolate layer, it must be rapidly and precisely cooled to lock in the texture and prevent bloom. The coated orbs enter a second cooling tunnel, this one longer than the first and broken into multi-zone chambers. Each chamber reduces the temperature by a few degrees, beginning at around 18 degrees Celsius and dropping to as low as 7 degrees Celsius by the end. This stepped cooling helps avoid thermal shock, which could crack the chocolate or cause the wafer interior to become brittle or absorb ambient moisture. Once fully set and stabilized, the finished chocolate spheres proceed to the final phase, the wrapping line. Unlike traditional bar-shaped chocolates, Ferrero Rocher's spherical format poses significant challenges for automated packaging. Each sphere must be individually wrapped in gold foil, creased along symmetrical lines, and sealed at the base, all without crushing or distorting the fragile chocolate shell. To accomplish this, Ferrero's wrapping system utilizes a series of robotic arms equipped with soft grip silicone actuators. These arms pick up individual spheres from the end of the cooling line and place them into pre-cut sheets of gold foil resting on vacuum-assisted form trays. Each foil sheet is statically charged to slightly lift its edges, allowing the robotic arm to nest the chocolate sphere into its center without displacement. Once placed, a mechanical rose press spins and crimps the foil around the sphere using concentric rotating plates, applying precise pressure to form clean, flower-like folds without damaging the surface. This wrapping process is performed at high speed, up to 300 pieces per minute, yet with micron-level accuracy. Foil alignment is verified by optical sensors, which detect reflective patterns and reject any pieces where the foil is torn, off-center, or folded incorrectly. Each wrapped sphere is then carefully lifted into a pleated paper cup, embossed with the Ferrero logo and treated with a micro-wax lining to keep it crisp and grease-free. After wrapping and cupping, the products pass through final quality inspection stations. Here, high-resolution cameras inspect every sphere for uniformity in size, foil fold consistency, and cup placement. Variations as small as 0.5 millimeters in height or misfolds in the foil pattern trigger automatic rejection and rerouting for manual inspection. Ferrero places high value on uniform appearance, as the product is both a confection and a visual symbol of luxury. At this stage, the chocolates are grouped and placed into clear plastic domes or rigid paper boxes, depending on SKU. Grouping is done by programmable robotic arms that align pieces into the iconic pyramid-shaped trays. Each tray is inserted into branded secondary packaging by automated folding arms, heat-sealed, labeled with batch codes and best before dates, and packed into master cartons for shipping. These cartons are then palletized, shrink-wrapped, and barcoded for traceability using a fully automated warehouse system. Once the Ferrero Rocher chocolates are fully enrobed, wrapped, cupped, and packed into their respective trays and branded packaging, they enter a post-production system that is every bit as engineered and precise as the stages that crafted them. This final section of the industrial manufacturing process focuses on how Ferrero ensures product longevity, freshness, safety, and global delivery, all while adhering to strict standards for sustainability, food safety, and visual uniformity. It is in this post-production phase that every element of quality assurance, logistics, and environmental control plays a crucial role in maintaining Ferrero Rocher's globally recognized consistency. At the end of the packaging line, finished boxes are conveyed into an area known as the atmospheric control and shelf stability checkpoint. This isn't merely storage, it's a climate-controlled stage designed to lock in freshness and prevent any deterioration before shipping. Although Ferrero Rocher does not require refrigeration, its chocolate and hazelnut content are sensitive to heat, humidity, and oxygen exposure. Thus, the packaging process incorporates passive and active protective methods. Each individually wrapped Ferrero Rocher sits in a waxed paper cup and is sealed with foil, creating a light barrier and reducing oxygen transfer. On a boxed level, the packaging is designed not just for aesthetics, but for product protection. The plastic domes and rigid cartons serve as microenvironments, shielding the delicate chocolates from moisture migration and aroma contamination. Many of these boxes are nitrogen flushed prior to sealing. This involves replacing the oxygen inside the packaging with food-grade nitrogen gas. The process is conducted in a low oxygen chamber using automated nozzles that inject nitrogen and heat seal the package in one fluid motion. This significantly extends shelf life and prevents oxidation of the hazelnut oils, which could otherwise lead to rancidity over time. Inside the post-packaging facility, all finished goods are held in a fully climate-controlled warehouse. The temperature is maintained between 12 degrees Celsius and 18 degrees Celsius with strict humidity control to avoid condensation or water activity that could degrade the chocolate or cause surface bloom. This facility is divided into inventory zones based on SKU, destination, and production date. Robotic pallet stackers and AGVs move products from the end of the line to designated storage lanes, which are connected to real-time digital inventory systems. Each pallet is barcoded and tracked with RFID tags linked to Ferrero's MS. This allows precise location tracking within the warehouse and connects the pallet's ID to batch-level data such as production shift, ingredient lot numbers, and inspection records. If a quality control concern arises, even weeks after production, the system can trace every individual chocolate back to the exact time, machine, and ingredient batch from which it originated. From this stage, logistics planning takes over. Ferrero Rocher products are shipped globally, and the logistics operation must ensure that every box reaches retailers in optimal condition, regardless of climate or shipping duration. For international exports, especially to regions with high ambient temperatures, insulated shipping containers or refrigerated trucks are used. These containers are monitored with onboard thermal sensors that log temperature data every few minutes throughout the journey. To minimize risk and ensure transport resilience, Ferrero's logistics systems include contingency protocols. If any deviation is recorded, say, a rise above 22 degrees Celsius for more than 2 hours, alerts are sent to distribution managers, and the shipment is flagged for secondary inspection upon arrival. If chocolate is exposed to unsafe temperatures, it may still appear intact, but could be structurally compromised or display bloom later. As such, these shipments are not automatically released and instead undergo retesting at the receiving distribution center. Distribution centers, whether owned by Ferrero or contracted third-party logistics partners, follow a standardized intake protocol. Every incoming shipment is verified against temperature logs and visual condition before being moved into inventory. Sampling is done on arrival. Inspectors randomly open retail cartons, remove individual Ferrero Rocher pieces, and subject them to quick checks for foil adhesion, paper cup deformation, and chocolate bloom. Any deviation from norm triggers a full line hold and a report to Central Quality Assurance. On a broader scale, Ferrero monitors product life and performance with a shelf life prediction algorithm that uses environmental exposure data, production variables, and regional velocity analytics. This allows the company to adjust shelf life claims and shipping cycles based on real-world data, rather than relying solely on laboratory simulations. It ensures that when a consumer opens a box, even after 8 to 10 months of storage, the product tastes and looks nearly identical to one fresh from the line. Simultaneously, efforts are being made to reduce the environmental footprint of this entire extended production ecosystem. Ferrero has pledged to reduce plastic use and improve packaging recyclability across all its product lines, and Ferrero Rocher is a major focus area. The familiar clear dome packaging, though attractive, is being redesigned with sustainability in mind. Research is underway to create bio-based plastic alternatives or entirely recyclable paperboard structures that still offer the same clarity, structure, and product visibility. On the energy front, the manufacturing facilities are increasingly integrating renewable energy sources. Solar panels are being added to plant rooftops, and waste heat from the roasting process is now recaptured through heat exchangers and reused in washdown systems or air heating coils. Motion sensing LED lighting, closed-loop water filtration systems, and advanced waste separation at the plant level ensure that the high-end nature of the product does not equate to unsustainable production. Even the hazelnut supply chain is now being restructured with long-term sustainability in mind. Ferrero's Farming Values Initiative works directly with hazelnut growers to implement traceability systems, promote biodiversity, and reduce reliance on synthetic inputs. Satellite data is now used to track soil health and pest pressure in real time, helping farmers reduce chemical usage while ensuring yield. These practices not only improve the environmental profile of the product, but directly contribute to the flavor consistency that is so critical to Ferrero Rocher's sensory identity. Finally, the company maintains a feedback loop from the consumer level all the way back to the manufacturing floor. Customer complaints or praise received via QR codes, customer service centers, or digital platforms are fed into an AI-powered insights platform. This system identifies emerging patterns, be it foil issues in a certain geography or flavor feedback in a seasonal SKU, and flags them for product review. If an actionable issue is identified, it can prompt retraining, supplier audits, recipe reformulation, or machine recalibration, depending on severity. Every step in Ferrero Rocher's journey, from the raw hazelnut fields in Turkey to the moment a box is opened during a celebration, is built on a foundation of precision, care, and control. It is a product that feels artisanal in experience, yet is undeniably industrial in scale. What emerges from Ferrero's vast, data-driven, sensor-monitored facilities is a confection that combines the warmth of tradition with the cold logic of automation, creating a gold-wrapped chocolate that is as technically impressive as it is delicious. Innovation, refinement, and global adaptation form the final layer of Ferrero Rocher's manufacturing ecosystem. While its iconic gold-wrapped hazelnut chocolate remains a symbol of indulgence and celebration, Ferrero's factories are far from static. Instead, they operate as dynamic, research-driven environments where new ideas are tested constantly, whether that's refining texture, adjusting to new market preferences, or introducing entirely new product variations. Behind every Ferrero Rocher lies not just tradition, but a relentless cycle of experimentation, data collection, and global customization. One of the most important hubs within any Ferrero Rocher facility is the Research and Development Laboratory. Here, food technologists, chocolate scientists, and texture engineers work year-round on small batch prototypes. These labs are equipped with micro roasters, pilot-scale enrobing machines, miniature tempering units, and lab-grade sensory booths. This allows for full-scale simulations of production on a fraction of the scale, enabling rapid prototyping without disrupting live manufacturing lines. One area of constant experimentation is the texture of the hazelnut cream filling. While the classic Ferrero Rocher contains a smooth, nut-forward Gianduja-style filling, consumer trends in some markets have shown preferences for creamier, milkier textures, or ones with inclusions such as wafer crisps, puffed rice, or even salt crystals. To adapt, R&D teams run side-by-side tests on fat ratios, alternative nut varieties, and natural emulsifiers. They analyze viscosity curves using rheometers and conduct accelerated aging studies to evaluate how texture changes over time under various storage conditions. R&D also works on flavor innovation. Though the classic Ferrero Rocher flavor is universally recognized, limited editions and regional exclusives are critical for keeping consumer interest fresh in high-growth markets. For example, in parts of Asia, Ferrero has tested matcha-infused chocolate coatings. In Latin America, dulce de leche fillings have been trialed. In the Middle East, formulations involving pistachio or rosewater flavor notes have been prototyped. Each of these requires adjustments, not just in recipe, but also in process. Certain fillings require higher thermal tolerance, others may react differently during enrobing or wrapping due to their moisture content. To ensure quality and consistency, each proposed variation undergoes extensive testing in the factory's sensory evaluation chambers. These are specially designed, soundproofed booths lit with neutral lighting, where trained panelists assess everything from first bite crunch to flavor release, melt rate, and aftertaste. They score samples against a range of criteria: intensity, balance, mouthfeel, appearance, and compare them to the gold standard classic product. Panelist feedback is digitized and overlaid with analytical data such as fat bloom index, water activity, and melt point curves to determine feasibility. Once a prototype passes internal tests, it must also be validated for scalability. Some ingredients or formulations work beautifully in the lab, but fall apart at industrial speeds or under prolonged storage. For example, Softer fillings may leak during high-speed rotation, inclusions may settle unevenly during conveyor vibrations, or certain coatings may discolor during heat sealing. The pilot line, an intermediate-sized mock-up of the full production line, is used to model these issues before any full-scale commitment is made. Beyond taste and texture, the factories must also accommodate aesthetic variations. Ferrero Rocher is synonymous with visual perfection. For seasonal lines like Ferrero Eggs, Valentine's Hearts, or Easter Nests, new mold tooling, wrapping foil textures, and carton formats must be developed. These new shapes aren't merely cosmetic. They change the product's center of gravity, its cooling requirements, and its wrapping dynamics. Engineers run simulations using CAD software and finite element modeling to ensure each new format can be safely and efficiently molded, coated, cooled, and wrapped without jamming or deformation. Each new mold also undergoes cycle time testing, measuring how many pieces per minute can be output while maintaining perfect quality. The aim is always to balance aesthetics with operational feasibility. For instance, a limited edition rose petal texture on the outer shell may look beautiful, but if it causes inconsistent wrapping folds or snags in the packing machine, it will be rejected or redesigned. Beyond internal product development, Ferrero Rocher factories must also localize production to suit regional regulations and consumer expectations. In some markets, ingredient restrictions may prohibit certain emulsifiers, sweeteners, or dairy derivatives. In others, there may be stronger demand for plant-based, organic, or clean label products. For example, factories supplying Northern European markets must comply with stricter labeling laws regarding palm oil and genetically modified ingredients. Ferrero addresses this with modular ingredient silos and real-time formulation control, switching between regional recipe variants without needing to rebuild entire lines. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components: a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase, baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from overprocessing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts, equipped with vision systems, scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds, Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal.